Alright my friends, welcome back to Frogboy X1 Gaming. I'm Andrew and today we want to talk about the new direct drive wheelbase that Thrustmaster will be bringing to the market on October 11th. So if you guys like this content, do not forget to like and subscribe. Now they dropped a paper today and that's basically what we're going to go over. It is a new era. So this is a new type of direct drive motor that Thrustmaster has has engineered. I mean, obviously, this is when we get into the paper, we'll hear about kind of the history of it. We'll talk about the current state of the direct drive motors are versus what Thrustmaster is bringing to the table and why they think it will be better, and it will be better for the sim racing community in general. Now, I've had a chance to read through this paper today, and if they can pull this off, this is impressive. This is very impressive. So without further ado, we're going to go ahead and we're going to jump into this. I'm going to go ahead and make my screen just a wee bit smaller so that we can actually get to the paper. I still want you to be able to see me. So what this is called is direct axial drive. You've probably seen that in the thumbnail or seen that in the thumbnail or title. The direct axial drive, unveiling the next generation of direct drive wheelbases. So let's go ahead and go to, is it going to tell me? Okay, 1, 2. So we're on page 2 now. I'm going to read this thing real quick just so you guys get an understanding. So a few weeks ago, Thrustmaster shared the first generation direct drive technology shared how first generation direct drive technology had many limitations preventing the creation of good, affordable direct drive wheelbase. We identified several pain points, such as the expensive amount of copper needed, the heat generated by the copper, and the associated difficulties with managing that heat, and the physical problems related to this motor typology, such as cogging and iron losses. We concluded years ago that the first generation of direct drive wheelbases could not meet our quality standards, our pricing aspirations for the entry and mid-level markets. And so we focused on finding alternative direct drive solutions, which led to the next generation direct drive technology. Today we are proud to present the industry's first and only direct axial drive, DAD, wheelbase technology, its advantages for sim racers of all levels, and how we expect to evolve in the future. So what I'm going to basically do, my friends, is this might take a little while to get through this. There's like 13 pages of this, but I'm going to read through it, and then I'm going to give you guys my input as we go through this. So sit back. This is pretty exciting, man. I read through this. All right, so the table of contents, obviously, this is going to tell us what is a direct axial drive wheelbase, better sim racing immersion and performance, how direct axial drive technology resonates with harmony, and so direct axial drive win. We're going to find out what it does, what it is, what it does, how it compares, and how it resonates with harmony. And then when it's coming out, which I already spoiled that, October 11th. So let's go ahead and get to number 4. All right, what is direct axial drive wheelbase? DAD wheelbases are made from a completely different type of motor called the Axial Flux motor. They are used in more in aeronautics, high-tech factories, and multiple high-end electric vehicles. By combining our years of expertise in sim racing, wheelbases, and technical knowledge of partners already developing axial flux motors, we were able to craft new sim racing wheelbases, which will outperform our initial high expectations. So we've kind of got, I'm obviously down here at the bottom. So design differences between axial flux motors and radial flux motors. Radial flux motors is what you basically have in your current direct drive wheels, in most motors that are on the market right now. They're really heavy. They're full of. So in our first new era paper, we went into detail about the radial flux motors used in first generation DD and how they were built. A stator tube made of a lot of copper coils surrounding a shaft, the rotor with many permanent magnets with many permanent magnets onto it. The shaft rotated depending on which coils you turn on. We called these motors radial because of the magnetism is radial to shift, meaning perpendicular to the rotation of the axis. All right, so an axial flux motor, on the other hand, is built in differently, and its design allows the magnetic flux to be parallel to the shaft in the rotation axis. This difference is key to obtaining a smooth rotation, sharper reaction times, and increased flexibility in motor scaling, and better electrical to mechanical performance. Everything that is required in a wheelbase, basically. So, if you look at these two pictures right here, this is the radial flux right here. So, obviously, you're going to have like your red, your blue, and every time these here are going to, when this side, like say you've got two wires coming in, one's going to energize one side, the other's going to energize the other side, which would represent the blue and the red. When you get the power sent to the blue, say it's turning one way, and then the other one's going to be turning the other way, you're going to get this, you're going to get this magnetic force that's going to shift every single time to make the motor, move back and forth. Is what this is showing for the axial flux is that instead of it being horizontal, like the shaft is horizontal, you're going to have all your magnets and all your copper and all of that stuff on what's called an armature that's going to spin. It's going to spin in there, and it's going to be like the magnets and everything are going to be horizontal. This is showing a vertical operation for how that plate, this is more like a plate instead of a shaft. This is more like a plate. Like all of this is going to contact like a pad or something like that. That looks cool. Like the next couple of pages are going to show us exactly. So let's go ahead. Axial flux motors were theorized a long time ago by Michael Faraday, 1791 to 1867, but they are barely sold to the public. It was always difficult to manufacture this type of motor at volume, and we've recently seen reductions in production cost. So as you can see right here, obviously this right here is going to be your this here is basically going to be like your armature or whatever. And instead of it like running like around or like your magnets or something, like I can't see much more because it's all freaking blurred out. Like I could kind of, theorize or whatever, but as you can see, like right here on this side, this is a plate as well. And then you've got like the green circuit board in here. Obviously this is just a blank circuit board in this part right here. You can't really see anything on there, but from what they describe in the paper is this, instead of the copper being in the windings on the on your armature, it's going to be imprinted in these boards or in this board or multiple boards or however they're going to do it. And as what happens is when these spin and they get the current, it's going to be able to sense that right on the plate as opposed to it going around in a circle. So let me just read a little bit more of this, and then we'll kind of talk about that. In axial flux motor design, the stator does not surround the rotor as it does on a radial flux motors. Instead, the motor is made up of many parallel layers along the shaft. It uses an ultra thin stator that is suspended parallelly between two rotors, supporting the permanent magnets. The copper coils are embedded directly into a circuit board. See, that's what I'm talking about, the copper coils. So no longer do you need that big, bulky, massive freaking wires. You get these right here that are just imprinted in the board, which, if this works the way they're talking about, this is going to be cool. So the copper coils are embedded directly into a circuit board. We've partnered with experts to tailor its patterns specifically for sim racing, allowing never before seen levels of precision, reaction time, and rotation speed. In fact, axial motors can output identical torque with only a fraction of the copper used by a radial flux motor, with the added bonus of being cogless. Now, when you have like a direct drive wheel, you sometimes you can feel like the cogging. Like I could feel the cogging when I was using like the Camus. It's not as bad on the Fanatec. It's still there every once in a while, but it's not like you're not feeling it. Like I understand and know what to look for. Like when this wheelbase actually launches and I get my patty cakes on it, I'll be able to tell, because you can tell it no matter how smooth your Fanatec or whatever is. Like you can feel the cogging every now and then. Added bonus of being cogless. Why? Thanks to the two parallel layers of magnets on either side of the stator, the magnetic field is used much more efficiently as less magnetic field is wasted, which is the case for radial flux motors as more than a half of magnetic fields go outwards away from the motor. Scaling advantages. Thanks to its design, axial flux motor scales much better than a radial flux motor, so increasing or reducing the output torque is more cost efficient. So that right there, that does sound good in theory. Like I understand this. I'm like okay, this actually sounds good in theory. In first generation direct drive radial flux, there were three variables to scale the power of the motor, which can be simplified this way: radial torque output equals magnetic force x length of the motor x radius of the motor squared. Because the magnets were only on one side of the copper coils and were placed along the rotor, in order to increase torque output, the radial flux motors had to increase both the length and the radius of the motor, both of which resulted in more copper usage. So essentially, the more like you want, like the more power the output, the longer the wheelbases get, or the bigger the wheelbase is going to get. That's why when you look at something like the Fanatec DD Pro, you got like this nice little square. Same with the MOZAs. When you start getting into the bigger motors, they start to get longer, like your Fanatec DD Pro or Podium, or your, Camus DDWB21, or even the, or like your Semicubes, they start to get longer versus, and I mean, they can get a little bit thinner too, but they do start to get longer as a result of needing all that extra copper to be able to actually crank up the power. So like the more you want, the bigger it's going to get. And where I work, we have some industrial size freaking giant motors and stuff that I mean, like your shaft is like 2 inches and stuff. Like these things are big, bulky, beastly things, and they're super duper heavy. So when they're talking about being able to reduce that to just a plate, or a circuit board with copper embedded into that, and then having both of the stators on both sides, both of the rotors on both sides, to be able to like kind of, create that friction or whatever, and be able to still produce that much of power. This is very, very cool sounding technology. That means you'll be able to get equivalent type power in a smaller, lighter base. It's actually going to be very, very good. If what I still kind of feel like the base is still going to be about the size of like your Fanatec, or even the size of the of the T248. So an axial flux motor has no magnetic field waste, as magnets cover both sides of the stator, so the length of the motor does not matter, and because its magnetic field usage is more efficient, the radius is much more important and scales better. This is the calculation of how it scales: axial torque output, magnetic force, plus radius of the motor cubic. Here's a quick illustration of the differences in scalability between the two motor typologies. So right here it's showing the green line that's going, that kind of just goes, and then it starts to separate pretty early on and kind of comes up to a higher and higher and higher, where the radial just kind of has like this 13 degrees, like it looks like about 13 degrees of like powered up. And this right here kind of just goes boom, and then it takes off more into like about 45 degrees. Like it just kind of boom, and it's like, whoa, you get like a lot more freaking, you get a lot more pretty quick, man. That's pretty good. Oh wait, how many did I just go down? Okay, by scaling more efficiently with no sacrifice to quality, axial flux motors can offer a cost-effective solution to make direct dive wheelbases more accessible to more sim racers. I wonder what this thing is going to cost, guys. Like I do, like I'm kind of curious. A cooler and more efficient wheelbase. Because axial flux motors use much less copper, our direct axial drive wheelbases generate much less heat and transform electrical power into mechanical power more efficiently. I've worked with a lot of motors at work. I do, and I've got like direct drive wheelbases and all of that stuff. And like I have yet to see this technology where I work. So I don't know, but this sounds like it would be this is making sense. Like it's making sense because these other motors, like I said, they're heavy. They come with a lot of copper. They're expensive. They get expensive pretty quickly. And so if this here, you know, the main component being the magnets are cheap. Freaking PCB boards cheap. The copper is the most expensive part of the manufacturing process of all of these direct drives and all of these motors and stuff. So if Thrustmaster really did find a way to deliver that punch. Oh, we'll get into more of this paper here in a minute. I just wanted to stop and talk about this. But if they can really deliver that 5 Newton meter plus experience this is gonna be good. And if they can bring this in at an affordable price range, this is going to be good. All right. In fact, first generation wheelbases used copper wires, 1 millimeter radius with a high linear resistance. Those resulted in great electrical losses via heat output, which massively impacted performance. It is true that the smaller the wire, you know, that you're using in your windings and stuff, they don't put out as much heat, but they do still put out a lot of heat. And then you get a lot of that resistance, and it really does kind of just, you know, start to bog things down even more or whatever. In our direct axial drive DAD wheelbases, which use axial flux motors fitted with ultra thin stators, there are no thick copper wires. Instead, we use thin lines of printed copper, 70 radius, or I don't know what the means. It's like microfarads or something. I don't know exactly what that means, but 70 radius or 0.07 millimeters, which is that's pretty small. But because of the more efficient magnetic power distribution, this reduced quantity of printed copper is actually more powerful than thicker copper wires. Now that's a bold claim. I'm not gonna lie. That's a bold claim, and I want to see this in action. Like, I am clearly freaking like, whoa, what the freak is this? I need to see this in action now. One of the primary reasons why axial flux motors went unused for so many years is that dissipating heat generated can be very complicated. Even if axial flux motors generate a lot less heat, this small amount still needs to be evacuated for it not to continue heating up until the temperature starts negatively affecting performance. The motor design does not naturally lend itself to dissipating heat and cooling down because all the components of the stator and motors are so close to each other that there's no airflow in the base. You simply cannot put a fan or casting radiator to cool it down. So with other bases, my friends, they have like I've seen motors that have fans on them and all kinds of stuff. You can definitely get a fan to blow down there between the freaking the armature and the housing and stuff like that. So you can usually dissipate heat pretty easily from those. This right here, they're talking about it being so close together that it's hard to get that heat in there. So is what they did to tackle the problem. Our direct axial drive wheelbases used patented solutions from a partner who founded the solution to evacuate the heat by adding heat pipes in the PCB itself, giving the wheelbase a passive, quiet, affordable, and innovative way to cool down while maintaining peak performance. Now that there, my friends, with the heat pipes, that might actually add to the overall size of the units themselves. If the heat pipes need to be big enough to, like, you know, and they got to encase all that and get these heat pipes in there so that they can actually dissipate the heat and stuff. That there's the one thing I could see adding to the overall size of the wheelbase. But I kind of feel like these are going to be fairly. I feel like they're going to be pretty small. I feel like they'll be able to get it. Better sim racing immersion and performance. While radial flux motors had inherent flaws that required a lot of workarounds to make motor feel good, axial flux motors are far more efficient, making those workarounds a memory of past generations of direct drive technology. This is where we're going to start getting into some incredible information and some incredible claims that I really hope turn out. Cogless motor, no more notching. In our first paper, we mentioned that cogging was a big issue in radial flux motors. When magnets and coils are not aligned perfectly, the magnetic forces make the wheel rotate on its own, both making the game information notchy and making you feel steps when turning the wheel slowly. With this first generation direct with first generation direct drive wheelbases, cogging was always artificially manipulated by complex algorithms that did their best to stick to the game information, but inevitably a lot of effects were missed because the algorithm couldn't compensate for impossible movements. The algorithm basically managed two types of force feedback and sacrificed a lot of information to offer authentic feedback experience. Static friction forces are the heavy forces which fight against you when driving. They require strong precision to avoid oscillation at all costs. Now, guys, oscillation on a direct drive wheel absolutely sucks. And if you get in there and you play with your settings enough, you can literally make these wheels oscillate so freaking bad. It's so annoying, and it really does suck. The more cogging a wheelbase has, the less the base can accurately turn the wheel, making movements to overcompensate the cogging that can lead the car onto the wrong trajectory. A cogless motor will always accurately align or accurately angle the wheel, meaning more precise control around corners as you manage your car's weight and adherence. Now, let me make it perfectly clear. My freaking Fanatec DD Pro, it aligns itself pretty dang good. Like, Fanatec is good. Like, they make some good stuff, and that's why I say, like, these things here, like all the wheelbases that I've used, like all the Camus, the everything I've used so far has been pretty good that way. But you can definitely feel some cogging and stuff like that. Like, you can feel, like when you're turning the wheel, you can feel when each ridge is coming up in that freaking motor. Like, you can feel that to an extent. Meaning more precise control as the weight and adherence out. And along straightaways where parasitic movements of the wheel can affect your trajectory. That's very true. Dynamic friction forces are the boost forces for the ones that provide all the little details you need. In a radial flux motor, even a perfect anti-cogging algorithm couldn't output a specific torque that provided a detail effect because the cogging would approximate all the values. So cogging or cogless axial flux motors will always output an accurate torque, providing more depth to the details, providing nuance and color to each individual piece of information. Our direct drive, hold on, let me get a drink. Our direct axial drive wheelbase reduces cogging by 99.99999% compared to all other direct drive DD wheelbases. Now, every freaking manufacturer says theirs are better than the others. Like that's it is what it is. On the market, at this value, the cogging is not perceptible to human touch, therefore considered non-existent, and it has zero impact on your sim racing. DAD is available to provide all the details in the game wants the player to fill. Being cogless means that the motor can angle the steering wheel accurately at any time with no more need for elaborate firmware or algorithms to artificially translate the game's outputs. Okay, now that, my friends, is an interesting claim. They're saying that they're not going to need, like firmware or algorithms or any of that kind of stuff because it just does what it's supposed to do. So I get that. Like, that's one thing that I absolutely want to see. Slew Rate, the game changer. We'll spell you the technical calculations, but basically what we're trying, when we're trying to perfect a motor slew rate, it's important to decrease inductance and increase resistance, assuming we can control the resulting heat output. Inductance defines how fast a coil can switch its polarity, primarily due to the number of turns the coils make. The key part is the key part of having a good slew rate. The less turns the coils have to make, the higher the slew rate as the motor reaches maximum performance in less time. So basically, if it doesn't have to, is what they're saying is if it doesn't have to move a whole lot, then it's actually better. I don't know. So resistance is essentially the force that counteracts electrical current. The higher the resistance of the coil, the higher the slew rate of the motor. But resistance will lead to increased heat output and its associated problems, loss of performance, deterioration of the materials, need of safety measures, etc. Why finding the right balance between inductance and resistance matters. We said we said we need a high slew. We said we need a high slew rate in a great sim racing motor. High slew rates mean more accurate details and faster reaction time. That's achievable when the motor's coils have less turns, a smaller cross-section area, and a longer length of wire. All while managing to dissipate heat while maintaining slew rate. It's pretty complex. We spent countless hours finding the perfect balance in our new direct axial drive wheelbase to provide an unprecedented level of motor reactivity for sim racers to react to all the details the game has to offer as quickly as possible. As a result, our DAD wheelbases react on average 2,000x faster than first generation DD could ever, changing the scale from milliseconds down to microseconds. With a direct axial drive wheelbase, the motor itself is no longer the issue in the latency setup. My friends, that is a pretty bold claim. I'm very interested to see how there's going to see how that's gonna work out. But there is some more stuff. Slew rate, the game changer. Oh, I think we were no longer issue faster. Okay, having an accurate position on a wheel and not being enough to the reaction time was not. Having an accurate position of the wheel would not be enough if the reaction time was not perfect. This is where the direct axial drive also shines. Our axial Flux motor delivers unprecedented reaction time thanks to its controlled overshoot capacity. Now this part right here, this is the part that actually really piqued my interest. So overshoot capacity, and they're going to explain all this, and then we'll talk about it a little more. In an electric motor, overshoot refers to the temporary excess of a desired target torque, quite literally the motor's power overshooting its typical constant range. This usually happens due to inertia as the system quickly calibrates itself to quick actions. Once a wheel is correctly aligned after a quick movement, the motor stops in the rotation, but the inertia of the complex system of multiple moving parts makes the wheel turn slightly more, overshooting its target value. This is why they talk about direct drive motors being dangerous, because that overshoot is can be sometimes if they go nuts and they go do more than they're supposed to. While overshoot is typically something the motor manufacturers try to avoid, we saw it as an opportunity to capitalize on a traditionally negative effect and turn it into a positive. When it's controlled, overshoot can actually enhance the wheelbase performance and immersion. A controlled overshoot minimizes the motor's response time. Embracing a slight controlled overshoot allows the wheel to reach its target torque quicker, providing drivers with an unbeatable control of the car's engine power. Now they show you it's like this little thing down here. Controlled overshoots also allow players to fill more feedback details in their wheel, including road imperfections, tire grip, etc. This means that a clear vision of how the car will react to both the track environment and the driver's actions. Keep in mind that we're talking about controlled overshoot here. All wheelbases have overshoot at some point, but first generation direct drive wheelbases were not responsive enough to control it. And when adding the effects of cogging on top of this, players would start to experience undesired torque ripple. You can accelerate to 10 Newton meters, it overshoots to 12, then overshoots the correction down to 9, then overshoots back up to 11, then 9.5, then 10.5, all in a matter of milliseconds, leading to microscopic speed and steering stabilization issues that gamers need to fight back against. Now, I haven't had one that's super terrible like that, but you can kind of you can kind of feel that a little bit. I think this is something that us, drivers that have had experience are going to be able to actually feel. This is stuff that I feel like we're actually going to be able to feel and adjust for and be able to, to measure. And I don't know how we'd measure it, but I think this is something that could potentially be measured. Some manufacturers try to counteract overshoot by slowing the rotation torque delivery before reaching the desired target Position torque. This helps to more quickly stabilize the output torque, but provides a damper feeling which many players, especially those competing at high levels, do not want, as it takes away the fidelity of the car's performance and information transmitted by the game, both of which can lead to a lack of anticipation. And you can really feel, like on direct drive, guys, you can really, there's a lot you can feel, and you definitely want those feelings. To make it easier to understand, try it yourself. When throwing a ball as far as possible with your arm, you could see that right when you release the ball, your arm keeps moving due to inertia. If you try to stop your hand at the exact moment you let the ball go, you will either need to dedicate some of your muscles as a counterforce to the natural inertia of your arm, or you'll need to slow down your arm before releasing the ball to reduce the initial the inertia, no overshoot, but the ball won't go as far. Controlling the overshoot is all about capitalizing on the benefit, reaching the target output torque quicker and providing an extra inertia-driven boost of torque while controlling its consequences, allowing for a higher initial overshoot to better use the motor's forces to stabilize faster back to engine's target torque. All right, so next generation direct axial torque, it shows the line kind of just going like shooting way up and then boom, back down just a little bit and then straight. Whereas like, you know, your first generation drive motors kind of have this like this like bouncing pattern, and then first generation direct drive with no overshoot kind of just shows that shaky balance where it's like this is saying that the Thrustmaster is going to shoot up, going to give you that torque, then it's going to come back down, it's going to overshoot just a little bit on the backward, back straight up, and then level out. Whereas the rest of these are showing that they are just all over the freaking place. That's pretty interesting. And this is something that like really, you know, kind of, if they can pull this off, that is very, very freaking awesome. All right. This is a comparison between the overshoot of our direct axial drive, the first generation wheelbases from our competitors, and you can see the controlled overshoot stabilizes the motor's performance far more quickly back to the motor's target torque. As a result, less unnatural counterforces to correct itself. That is cool if you don't have to overcorrect a lot of, you know, the wheel trying to, that, yeah, like you can feel that stuff. And yeah, in our tests, we achieved controlled overshoots that were up to 107% the amount of the constant torque. As mentioned in the first paper, do not forget that the peak and constant torque are two different things. The peak torque is how much you feel the details, while the constant torque is how much force you must physically provide to the wheel to turn the wheel. A direct axial drive wheelbase that outputs at a constant 5 Newton meters of torque will always require the same physical force, no matter if its peak torque is 8 Newton meter, 15 Newton meter, or higher. Saturation, what's that? In the previous paper, we explained the first generation direct drive would saturate quickly, either because the game detected that the wheel couldn't output what it was asking for, which is called clipping, or because the radial flux motor suffered iron loss, a mechanical limitation generating eddy currents. While game clipping can be managed in the game settings, iron loss was a physical limitation of the first generation wheelbases. However, because our axial flux motor uses direct magnetic field, we considerably reduce eddy currents. Eliminating eddy currents eliminates parasitic movement and reduces the heat generated, both of which help the wheelbase better translate the game's details thanks to sharper peak torque. Peak torque of a direct axial drive base goes much higher than the first generation DD wheelbases of the same constant torque. However, the overall curve is much more detailed. You may wonder if reducing the overall feedback strength of a strong first generation wheelbase, example, a constant 25 Newton meter direct radial drive base reduced to 5 Newton meters, would give you the same results. If we take aside the technical challenges required to manage cogging, it could, but it would require rare and expensive materials to achieve the same kind of performance. So they're saying that it is possible to do this, but yeah, it would be expensive. How direct axial drive technology resonates with harmony. Now, this was the second part that I was like, oh my gosh, dude, this sounds pretty cool. Did you know that many industry innovations were discovered accidentally? Penicillin, X-rays, dynamite, microwaves, cornflakes, Well, now Harmony is one of them. So let's see. To test the accuracy of our direct axial drive wheelbase in achieving target torque, we wanted to see how fast a 5 Newton meter constant torque direct axial drive wheelbase could vibrate and still control the resulting overshoot, switching from 5 to -5 Newton meter over and over, faster and faster, up to the point where we were measuring erratic values. With overshoot so high, we thought we broke our test bench, so we reinforced the test bench and tried again with the same results. Here is what we observed that day. So it's showing that, all right, yeah, that looks cool. We realized that for the first time, sim racing wheelbase resonated. We mean it literally resonated. What is a resonance phenomenon? When an object vibrates, it's at its natural frequency over a longer period of time, it starts experiencing higher amplitude of vibrations without the need to increase the input force. Need help visualizing this resonance? Imagine bouncing on a trampoline. Because you fall from a higher position on your second jump and your third jump, you will go even higher. This is exactly what happens in our direct axial drive wheelbase. Basically, the stator acts as a trampoline, and at the right frequency, it vibrates perfectly in sync with the rotor that helps it change direction, similarly to a slingshot effect, and overshoots its target value. This phenomenon was discovered by physicists and mathematicians a long time ago, but since first generation DD could not vibrate that fast due to eddy currents again, we never thought direct axial drive bases would be able to resonate. When resonating, the controlled overshoots reach up to 150% of the constant torque. For example, when maxed out, 5 Newton meter wheelbase generates more vibrations than a TGT2 transducer in the same frequency range. What it brings to sim racing. We quickly realized the phenomenon could be a cool feature in a wheelbase when controlled. Resonance can amplify specific effects and give enhanced haptic feedback to the player when an important event happens: car collision, gear shift, curbs, etc. Because our direct axial drive motors do not saturate, we are able to give an extra layer of information to the player as the wheelbase outputs at a constant torque. This is where things get interesting. If this is real and this works, oh my gosh, could you imagine that? Like, no more clip-in, and you're getting all that freaking like feedback, like you're feeling the gravel, you're feeling everything. Oh, this sounds so freaking cool. And this is one of the things that has me super excited for this new direct drive wheelbase. Once testing this feature as a gear jolt, for example, we heard from multiple people say the same comments. Did you put a butt kicker in the seat? Or do the pedals have haptic feedback? Of course not, but the vibrations from the bass propagate through the cockpit, giving drivers sensations they never felt before in sim racing. Once this feature gets integrated into games by developers, it will bring an even more immersive experience out of the box without the need for extra vibrations modules to your setup. That is pretty cool, man. Like, obviously the developers are going to have to integrate this, but that sounds cool, and I am excited for that. So, direct axial drive win. Direct axial drive will be the new sim racing standard. It simply outperforms first generation direct drive wheelbases in every category at a price to materials ratio that scales more efficiently and affordably. Our paper's purpose is not to convince you, but to explain the change and why it matters. Sometimes reality gets lost behind appealing marketing terminology, and we believe it's important to explain that even if direct drive DD and direct axial drive share a similar name, they are based around completely different motor technology. Thrustmaster will present the industry's first direct axial drive DAD wheelbase on October 11th. We don't expect it to be the last, because a new era of sim racing has begun. Don't miss the opportunity to be the first to discover it. Subscribe to our newsletter, follow us on our social media channels, and join the discussion on Discord To get all details, if you want to be the first to try the upcoming direct axial drive wheelbase, you can visit our booth at ADAC Sim Racing Expo, October 18th, 19th, and 20th. See you on the track, Thrustmaster team. So, that there's the paper, my friends. That there's what we're talking about. Let me get back over here into this. Let me make this a little bit bigger for this for me to close out. Guys, this, I don't know. Like, I'm excited. I'm pretty happy about this. I want to get this thing in my patty cakes. I want to check it out. I want to put it through its paces. I want to run it around. I recently just picked up a Thrustmaster TGT2. I paid for this with my own money, and then I also bought the R32 rim. This is Thrustmaster's, you know, like, this rim here, you can take the rim off, you can put new rims on it, all of that stuff. It's got more customizability than anything I think I've ever seen from a Thrustmaster product, so that's cool. It does have both of the quick release things for both the the T598 plus your old style. So I bought that. I'm going to be testing that Thrustmaster TGT out over the next little while, putting that thing through its paces. I do plan on doing like content, like one day I'll just like pull up the seat and I'll have the TGT on it. I mean, honestly, guys, I've wanted a TGT ever since I first started sim racing, but I just was so unsure about spending that much money on sim racing equipment. But now it's like, I just wanted one to say I bought one. I just wanted one to say I bought one. So, all right, guys. We'll see you in the next one. Thank you so much for freaking watching today. This was an awesome video, and we'll see you guys later. Thank you so much.